So welcome friends. In this section, we are going to learn a new generation's CPU core sections, and in this sections we are going to learn how the CPU core voltage is generate for the new generation laptops, and then after we'll learn how to read the schematic diagrams and what are the test point if our CPU core voltage is not generating. Okay. So the CPU core voltage is a final voltage for the CPU, and before CPU core voltage there are number of voltages are generated like 5 volt, then 3 volt, and then 1.8, then 1.2, and then 1 volt, and then 2.5, and then zero point 0.6. There are number of voltages are generated, and all these voltages are going to the related component like PCH or the bias, or the here is a PCH is a combined, like the CPU and the PCH is a combined, but still those PCH voltage is going to this chips. So that is why it's called the SOC. SOC stand for system on chips. That means everything is there on this chips. Okay, so all these voltages are generated, and then the all voltages are generated finally. Then the CPU, this VRM chips get one signal, and that signal is called VCCST power good. Okay, so all things we'll learn step by steps, and then we'll go to the schematic diagrams and we'll see how to read the schematic diagram. So here is this buck converter which responsible to generate the CPU core voltage. Now here is a single buck converter is here. In last CPU core section, in the old models of the CPU core section, we saw there the number of buck converters are there. For one is for the graphics core, then two are for the CPU core. It's because of that the technology is old, and the MOSFET size is called the nanotechnology. It's called the TDP, and that is very high. That the MOSFET size is 48 nanometer. It's called the NM. But the newer generations laptops motherboard and in their CPU, the MOSFET size is very less. That is somewhere around 10 nanometers. Is called a 10 nm. The TDP is very low. So that is why the CPU core current is very less, because in older model the CPU current is required something around 30 ampere, but this newer generations CPUs require hardly a 10 to 15 amperes currents they require. So for that, here is a single chip buck converters only use. There is no need of multiple buck converters. Okay. So these are the two MOSFET, then the coil and the capacitor, and to drive these two MOSFET, these chips, it's called the VRM chips, voltage regulator models. And normally for this VRM chip they use ISL. Okay, and what are the things is required to run these chips? First is require the power, and this MOSFETs require the 19 volt, this 19 volt or 18 volt, which were coming from the adapter which come across this drain. And normally these MOSFET are the N channel only. In most of the cases this MOSFET are the N channel only, so that is why the drain voltage is 18 or 19 voltage. Okay, and this chips require a 5 volt at it VCC or VDD, but in newer generations VRM chips require a 3.3 voltage also, so that you have to check. So now this VDD or the VCC, that is a supply voltage for this VRM chips, require a 5 volt. Then this 18 volt is the drain. VRM chips got this signal, and that signal is called VCCST power good. The VCCST power good stand for the all voltages are okay, like the 3.3, 5, 1.05, 1.8, 1.2, 0.6, all voltages are stable, and this signal saying to the CPU that your all voltages are ready. Okay, and then this VRM chips ready to work, but before that he checked the temperature, and here is the NTC is called the negative temperatures coefficient, is one kind of thermistor who responsible to monitor the area of the temperatures, area of the motherboard's CPU side. If the temperature is high near the CPU, then NTC inform this information to the VRM chips, and then the VRM chips terminate the core voltages to cool down the motherboard. So this is a basic idea of the NTC. And if the temperature is high, then here will be the VR hot signal will be the 0 volt. Okay, and if the VR hot output signal if 1 volt, then the temperature is a normal. So you have to make sure how much VR hot signal is coming. It's supposed to be a 1 volt in normal temperature. Okay, so here's output is 1 volt, then the 5 volt is here, and there is a one more signal is called vsense. The vsense is a signal is coming from the CPU to the VRM chips. It's a signal detecting the CPU. That means the VRM chips detect whether CPU is there or not, CPU present or not, and that signal is called the vsense. And the vsense, and if we check this vsense on buzzer mode, remove the power and put your multimeter on the buzzer and put your one probe to the ground and another probe to this vsense pin, then you will get a buzzer at very less resistance. That means the CPU is present, CPU is there. And if the resistance is high, and if you remove the CPU from the CPU's here, then here will be no resistance. Okay, so that is the basic idea. So here the resistance should be the 0 at the vsense pin, then this VR out signal should be output at 1 volt. Here is a VCC, that is a 5 volt, and then this VR on signal, this is the input signal, that is also from 1 volt to 3 volt, this is the input signal, and this is a input signal saying to this VRM chips to turn on their buck converters, now once these chips get this enable signal from the SIO, then this chip started switching this two MOSFET. Here are the two MOSFET connected in parallel to each other. This is the upper MOSFET and this one is the lower MOSFET. This side is a drain, then the source, and this MOSFET is a drain. So the source and drain are connected to each other, and this the lower MOSFET source is connected to the ground, and the junction is connected to this coil, and the coil output is connected to this filter capacitor. Here's a filter capacitor, and then this voltage entered into the CPU. That voltage is called the CPU core voltage. Okay, so now once this chips get the enable signal, then he started switching this two MOSFET. Okay, started switching this two MOSFET, then this 18 volt or 19 volt started switching, pulsating AC voltage will be generated across this MOSFET, and this voltage is going to the coil stop the AC voltage, pass the DC current, and that DC current is going to the capacitor, filtered by this capacitor, and this voltage goes to the CPU, and this voltage is supposed to be a 1 volt approximately. So here the output voltage somewhere around 1 volt, it's going to the CPU. So CPU got the power, then CPU start functioning. CPU have their own power management department. Once CPU receive the power from the VRM section, then he react and generate this SVID signal. Here is the SVID signal stand for VID stand for voltage identification signal. That means once the CPU receive the power, then he check all those power and inform to the VRM chip whatever the power he got is perfect or not. If he got a less power, then he inform I need a more power. If he got a more power, then he inform to this VRM chips I reduce the power. So this types of communication take place from CPU to VRM chips. So once this VRM core voltage generate the CPU core voltage, and this voltage is going to the CPU. After that, the CPU start communicating with the VRM chips via this SVID signal and inform how much current is required to CPU. Whatever the requirement is, CPU inform to the VRM chip, and this signal we can check by using oscilloscope. We can't check this signal on the multimeter. Okay, so this is called the VID signal. And after this VID signal, If when the voltage stable, the CPU core voltage stable, if everything is normal, after that this VRM chips omit one signal, and this signal is called the VRM power good. This VRM power good stand for the core voltage is stable, the CPU core voltage is ready, or sometimes called the V gate, and this is called the output signal coming out from the VRM chips, and this voltage will be somewhere around 3 volt. So friend, in this way the CPU core voltage is generated. Now we'll see how we'll read the schematic diagrams. So here I open a schematic diagram. The model number is LA911. This is a Skylake processor, and this section is called the VRM section. This core voltage is there. It's written here. This motherboard is a Compal motherboard. Here is a Compal motherboard. You can see here at the corner it's a Compal motherboard, and the motherboard model number is LA901, and this page is called the VCC core voltage, or it's called the CPU core voltage. So now how the CPU core voltage will generate, we'll see, we'll learn how to read the schematic diagram. So this is a VRM chips, and these are this MOSFET. Here is a dual MOSFET. That means in single MOSFET there's a two MOSFETs are there. It's called the dual MOSFET. In the single chip there are two MOSFET. Okay. So now this is a MOSFET get 19 voltage from this pin. From this pin it's called the power SRC. The 19 voltage passes and is entered into the pin number 5. It's called the VIN pin, and then here is my VRM chips. The VRM chips, the location number of the chips is PU500. This is the location number, and the chip number is TPS 51624. Okay, the what is the number of the chips? It's TPS 51124 RSM. The TPS means this chip is a Texas Instrument. There are, I already told, there are number of manufacturers are there who making this power chips. One is ISL, then is a Richtech, then is a Maxim, and then is a Texas Instrument. So here the Texas Instrument chips are used in the power CPU core sections. So now the first thing is these chips require a power. So this is a pin, VDD is a pin, and this is a power pin, and here the power voltage is a 3.3 voltage is coming from 3.3 voltage section. So 3 volt is coming via this resistor. This resistor's location is a PR519, and the value of this resistor is a 1 ohm, 5% is a tolerance, and this 3.3 volt entered into the pin number 2, and then 5 volt also required at this pin number 28, and this 5 volt is coming from the always section via this resistor. This resistor value is a 10 ohms, resistor location is a PR 526 and entered into the pin number 28. So at both pin you have to check this two voltages. Here you have to check 3 volt, and here you have to check a 5 volt, and there is a VR hot signal. This one is a VR out signal at pin number 30. So this is output signal is coming out, and its signal name is become a pro hot or the H pro hot. So here supposed to be a 1 volt if the temperature is a normal. And who is responsible to measure the temperature? So there is called the NTC. So this side is a NTC is here. How to find the NTC? Simple, find the NTC. So see, here is a resistor, and what is the value of this resistor is a PR505, and what is the value of so this is a location number. PR505 is a location number for the resistor, and the value of this resistor is a 10 kilo ohms and 5% tolerance. So here also something kind of resistor also there, but here is a circle around this resistor, so that is why it's a NTC. Simple, how to find the NTC? On the schematic diagram there will be the zigzag line like a resistor, and around that those zigzag line there will be a circle like this. So from that we can come to know this is a thermistor, And what is the value of this thermistor? This value of this thermistor is 100 kilo ohms. Okay, and 1% tolerance. So at the normal temperatures, the value of this thermistor is 100 kilo ohms, and as soon as the temperature is increasing, the value of this thermistor is, or value of this antis is decreasing. Okay, and this value is going to this pin is called the therm, pin number 13. Okay, so these are the input criteria, and now the chips got this power VDD, and temperature is also normal, and then this chips got this enable signal, and this pin is called the VR on, pin number 8, and this signal is coming from page number 15. So this is called the page number. This signal is coming from the page number 15, and the name of the signal is H underscore VR underscore EN. So this signal is called the VR on signal. Okay, and how much the voltage will be there at the VR on? You will get from 1 volt to 3 volt. Okay, and this signal is coming via this resistor. It's called the PR50536, and the value of this resistor is 0. So this VR on signal is coming, and this give enable to this pin number 8, that's called the VR on signal. And as soon as this VRM chips got this VRM signal, then this started pulsating these two MOSFETs, which is here this location is a PU501. I already told that this MOSFET are dual MOSFETs. That means in single packet there are two MOSFET, and this signal is coming from this VRM chips, PWM1, PWM1, and started triggering at this two MOSFET at pin number 8, and the pulsating AC voltage will be generated, come out from the pin number 4, and is going to this coil called the PL500, and then this voltage is filtered by the capacitor. There are a number of capacitors are here, started filtering, so these are the capacitor, and then the CPU core voltage will be generated at here. It's called the VCC underscore core. So this is the output voltage, and here we will get somewhere around approximately 1 volt. So this is the output voltage. Okay, so as soon as this voltage is stable, VID signal also there. Once CPU got the power, then CPU started communicating with this VRM chips. You can see here VID alert, VID clock. Okay, so these are the signal which is going to this VRM chip, started communicating, CPU started communicating, and asking CPU how much voltage or current is required. And then once this voltage is stable, then this VRM chips location number is 500, chips number is TPS51624, generate the power good signal from pin number 3. Pin number 3 is the output pin, it's called the P good. The P good is the output, it's called the power good, and this power good is going to the page number 15, and the name of the signal is H underscore VR underscore ready. That means the CPU core voltage is ready, and the voltage will be here somewhere around 3 volt. So this is the output signal, and if this signal is come out from the VRM chips, that means our entire section is working fine. Okay, so friend, in this way I explain how the CPU core section work. I explain the concept how the CPU core concept work, then I explain how to read the schematic diagram. I hope you understand this concept. Thank you very much.